Okay, good morning to all of you. In our last class, we have been discussed about multinomial distribution and how it has been connection with binomial distribution. Also, we have been discussed and the PMF of multinomial distribution, how it will be this much. We have been discussed with the help of uh, 3-4 examples. That is your rolling of dice 2 times, tossing of coin 2 times, rolling of dice 4 times, and another type, one different type of problem, that is your red, blue, and green ball. From that, we have been in detailed. We have been discussed that how the PMF will be this much and how uh, in which way this distribution, multinomial distribution, will be connected with binomial distribution and how it is a generalization of binomial distribution. That also we have been discussed. And in our today class, as I told, that we have to discuss moments and moment generating function of multinomial distribution, because moments are essential to find out the uh, expectation value, variance, covariance, etc. And here also, at last, I will show you that how uh, again from the moment generating function also we are going to be conclude that this will be the generalization of this distribution, will be a generalization of binomial distribution. Okay, so here, for in this case, in your multinomial distribution, the most important thing is that the outcomes of a trial will be more than 2. Here, more than 2, but in case of binomial it is 2. For each trial, the outcome, if more than 2, then we are going to be say that that is your multinomial distribution, but if it will 2, that will be called as your binomial distribution. Okay, now we have to start the moments and moment generating function. But before to start the moment and moment generating function of this distribution, first of all we have to just revise whatever we have been studied in our previous classes. Okay, whatever we have been studied, because this is most important. Okay, uh, because you can say that your expectation value, your variance, your covariance, these all are belongs to your moments. Okay, so how these all are belongs to moments, that we are going to be conclude in our discussion. uh, so in our previous discussion, what we have been studied it, expectation in case of one dimensional random variable, expectation of a random variable is nothing but x summation over in for the discrete, so summation over x into PMF, that we know. And this expectation also can be represented as x bar or equal to mu. Okay, next, variance is represented as v capital X. Here this is your 1D RV, random variable. Okay, this is nothing but expectation of 1 minus x bar, means 1 minus mean. Okay, whole to the power 2. Here this will be summation over x, sorry, x minus capital X minus x bar whole square, that will be x minus x bar whole square into fx. Okay, that is your PMF. And here this, if we are going to simplify this one, then we can found expectation of x square minus expectation whole square. Okay, these things we have been studied. If we are going to consider 2D RV, two dimensional random variable, we have been studied that covariance of covariance between two random variables x and y is nothing but expectation of, careful you have to watch. Okay, x minus mu1, y minus mu2. Here mu1 and mu2 are the expectation of x and y respectively, or we can write expectation of x minus expectation of x into y minus expectation of y. So here I written that mu1 is nothing but expectation of x or x bar, whatever written over here, and mu2 is your expectation of y or y bar. These things we have been discussed in detail. Okay, so if we are going to simplify this one, we can found the covariance between x and y is nothing but expectation of xy minus expectation of x into expectation of y. So here you can see that this is the expectation of two random variables, and the name of this expectation that we are going to be discuss in this video. Here expectation of xy is called as fast and fast product moment. You just remember fast and fast, and these things also we are going to discuss. See, in detail we are going to discuss. Actually, what happened? No, you in our syllabus bivariate distribution was not there, so I leaved that one. But here in this class we are going to discuss. Okay, so here you can see that expectation of x y is called as your, if here x to the power 1 y to the power 1 is called as a fast and fast product moment about origin of random variables x and y, that we are going to discuss. You just wait. Okay, so here this is your fast and fast product moment of x and y about the origin. And also we have been discussed regarding moments, that is your one for 1D random variable, rth moment about a point is nothing but expectation of x minus a to the power r. If it will be origin about the point, that point will be origin, that here we have to put a equal to 0, that will be expectation of x to the power r. Here x, remember that this is x is represent the random variable. Okay, and this is represented as mu r dash mu 1 dash mu r dash. Okay, so now if r will be 1, then this will be expectation of only x to the power 1 means x. This is nothing but mu, instead of r we have to write 1 dash, that is nothing but expectation of x. So first moment about the origin, carefully you have to watch my language. First moment about the origin of 1D random variable is automatically called as its expectation. Okay, so expectation of a 1D random variable, that means first moment about the origin. Okay, so here moment, variance, covariance, these all are the so-called moments. Okay, expectation, variance, covariance, these all are one moment. Okay, so here expectation is nothing but called as your first moment about the origin. Okay, now second moment about the origin, if we want to find out, what we have to do, we have to put r equal to 2, that will be expectation of x square is represented by mu 2 dash, right? Now vx, the so-called variance, will be, variance is how much, ex square minus ex whole square, will be ex square minus ex whole square. That means second moment about the origin minus first moment about the origin. Okay, you got my point. This is also represents moment properties. Okay, the second moment about the origin minus first moment, I will be get automatically the variance. Okay, so here second moment, or mu 2 dash minus mu 1 dash whole square, right? These things we have been studied. In detail we have been discussed. You can check your note, no problem. Now, rth moment about mean, central moment. What is the central moment? This is represented as mu r. Here about the origin means it will be mu r dash. If dash is not there, then it will be represent the central moment or rth moment about the mean. See, if we have to consider moment about a point, that means expectation of x minus that point to the power r. So here, instead of about any point, if we are going to consider expectation value of x itself, then here instead of a, I have to write expectation of x. Simple. So expectation of x is nothing but your x bar or mu, anything you can write. These are the different representations only. Okay. So here we can write that about the mean or the so-called central moment is nothing but mu r equal to expectation of x minus that point. Instead of that point will be written as x bar, and we know that expectation of x is a constant, okay, as like a point, which is represented also by x bar. So x bar to the power r. This is your rth moment about the mean, okay, or the so-called central moment, right? Here if r equal to 2, suppose we have to consider r equal to 2, we have to put r equal to 2. That means expectation of x minus x bar whole square. So here x minus x bar whole square is what? Already we have been discussed that is the so-called variance. Okay, so here the variance, whatever we have been discussed, expectation of x minus x bar whole square, this is nothing but your second moment about the mean. You got my point? See, here your expectation of a random variable is nothing but your first moment about the origin. So either you have to tell that your first moment is required of a random variable, or you can say that you need the expectation of that random variable. Both are same, okay, different language. As I told that the expectation, variance, covariance, all are the moments itself. Okay, so if r equal to 2, that is nothing but second moment about the mean. So mu 2 is nothing but the so-called variance. So here second moment about the mean is nothing but represents the variance. That is your second moment, or mu 2 is written as ex square. If you are going to solve this one, you will be find, see, this one we can find this one, this the detail steps to solve from here to here, all the steps we are done in our class. Okay, so mu 2 will be, we can get this one. So this is your second central moment of the random variable, is called as the its what, its variance, right? And your expectation value of the random variable is nothing but moment about the origin. Okay, now moment generating function we have been studied, that is your m.g.f about a point A. See, why we are discussing these previous discussions, because these discussions are needy for our today's class. Okay, so carefully you have to watch. See, m.g.f about a point A. If we are going to consider moment generating function at a point A is nothing but m x minus a into t about A is nothing but expectation of e to the t into x minus a. If that point is your origin, mgf about the origin, so instead of a we have to write 0. So this will be expectation of e to the power t x, that we know. Here I'm going to just expand this one, e to the power tx. If we are going to be expand, then we are going to be found expectation symbol is here. bracket 1 plus tx by 1 factorial plus t square x square by 2 factorial plus tq x cube by 3 factorial and so on tr x to the power r by r factorial and again so on. So here mxt, if I am going to be operate this expectation to all the terms, then expectation of 1, expectation of this one, expectation of this one, expectation of this one and so on, expectation of this one and so on. And we know that expectation of a constant is that constant itself, that we know. Suppose expectation of a constant is that constant itself, that we know already. So here expectation of 1, so expectation of t by 1 factorial x, if I will operate t and 1 factorial, both are constant because here the variable is x. So t by 1 factorial taken outside, expectation of x. Likewise here t square by 2 factorial, expectation of x square, t cube by 3 factorial, expectation of x cube and so on, t to the power r by r factorial, expectation of x to the power r and so on. So here you can see this mxt can be written as in the summation format as r equal to 0 to infinity t to the power r by r factorial mu r dash. How? See, you just expand it. What you are going to get? You are going to get, put r equal to 0, 0. You are going to get mu 0 1. So here mu 0 1 means 1. So this will be 1. Then you have to put 1, r equal to 1, t to the power 1 divided 1 factorial. This will be 1 mu 1 dash, mu 1 dash, and mu 1 dash is what? Mu 1 dash is nothing but your expectation, ex, right? 2 dash, t to the power 2 by 2 factorial, 2 dash is nothing but e x square and so on. So hence this series can be represented by summation format, this one that we know. So this is nothing but this mu r dash is nothing but expectation of x to the power r, or this is your rth moment about the origin, and this is your mu 1 dash nothing but your expectation. So if we can write this expansion, the coefficients will be give one moment about the origin. So this coefficient t by 1 factorial, these things already we studied, okay? T by 1 factorial coefficient of t by 1 factorial is nothing but first moment, or this is your expectation, or you can say. And coefficient of t square by 2 factorial is your second moment about the origin, okay? Then coefficient of your t cube by 3 factorial is your third moment about the origin, and coefficient of your t to the power r by r factorial is nothing but your rth moment, mu r dash rth moment, okay? So this is one method that we can find out the moments about the origin, okay? And also another method is that we have to consider the derivative. So rth derivative with respect to t at t equal to 0 will be give you rth moment about the origin, Now you just consider r equal to 1. If r will be 1, your mxt is your this one, okay? So first derivative you have to consider, this will be the constant will be 0, this will be how much? If we are going to consider d by dt of this one, then this will be, this coefficient will be 1, and you are going to get ex only, expectation of x. Then second term will be 2t by 2 factorial ex square, third term will be 3t square by 3 factorial and so on. You can see except this term, other terms contains t after taken first derivative of mxt. So after taken first derivative with respect to t of mxt, we got this term is only t free. There is no t after derivative, but other terms will be contain t. So whenever we are going to put t will be 0 after first derivative, these terms will be 0 and we are going to get ex only, expectation of x. So that expectation of x is nothing but mu r dash. Okay, so we can get the first moment about the origin. Likewise, if you want a third moment about the origin, you have to uh, uh, mm, consider the third time, three times derivative with respect to t of mxt. After that, you have to put t equal to 0. You are going to get third moment. Like for the rth moment, you have to differentiate mxt rth time, and then you have to put t equal to 0. You are going to get this one, rth moment, right? Rth moment you can get. But if first one time you have to consider the derivative of mxt, this will be mu 1 dash, that is not more first moment about the origin. These things we have been studied or discussed in detail, and with the help of these concepts, by considering this concept, by expansion concept and this derivative concept, we also found the moments of binomial distribution, Poisson distribution, geometric distribution, negative binomial distribution, hypergeometric distribution. For all these distributions, we found the moments uh, and its expectation value, variance by considering this expansion format, and by considering this derivative format. Both the format we have been done at that time for all the distributions. But here in this case, we are going to discuss about the multinomial distribution. For that, here you can see that whatever we have been discussed, that is a single random variable. Okay, single random variable x is there. If we have more than one random variable, then how we are going to handle those things. So for that, as I told that this moments of bivariate distribution was not in your syllabus in your second unit, but here I'm going to be represent. You can write extra for your note, no problem, because it is required to understand the moments of the multinomial distribution. Okay, so carefully you have to watch. So here, as per the definition, you can see, let 2D, first we have to consider 2D RV, random variable. So consider 2D random variable as x and y with PMF is your fxy or pxy, you can say. Then the expectation of a function gxy belongs to RV's x and y can be written as expectation of gxy. See here the two random variables. Here we written gxy means here x and y may be like this, x plus y or xy or x square plus y, anything. Okay, uh, mm, only for that in general we written gxy will be equal to summation over I, summation over j, gxi yi and pmf. So if we have the two random variables, then the PMF will be x equal to xi intersection y equal to uh, yj, that already we have been discussed. Okay, so here I can show you, you just go through your note whenever we have been discussed this table, that x is one random variable, y is one random variable. This is represents the probability, uh, that is your x equal to xi intersection y equal to yj. So here x varies as xi and yj. In detail we have been discussed. Okay, so this each and every points in the table is represents the so called x equal to xi intersection of y equal to yj. If discrete, if it will be continuous, then gxy double integration we have to consider gxy into fxy dx into dy. Okay, now if for the continuous case, if we are going to consider this gxy is nothing but in the form of xy, x into y, x into y. Okay, so here also gxy we consider that x into y, then expectation of x into y will be how much? Summation over I'm telling about the discrete one. Okay, because as we are discussing the multinomial discrete random variable, so expectation of xy will be summation over I j xi yj, and this is the so called PMF. Right, now we are going to consider the moments here. From this point, carefully you have to watch the rth and sth. Now this is s, written as s, not 5. It is looks like 5 but it is s. Okay, the rth and sth product moment about origin of the random variable x and y respectively is defined as, see, previously for a single random variable it is written as the rth moment. Okay, rth moment, rth moment about the origin, but here as we have two random variables, so it will be called as rth and sth. For this random variable may be rth, and for this random variable sth. Okay, any number, this is any number, this is any number, starts from 0, and also called as rth and sth product moment. This is here for the single random variable it is called as the only moment about the origin, but here it will be called as the so-called product moment about origin of the random variables x and y respectively, defined as what? Mu rs dash. For single random variable is what? This is your mu r dash. Here mu rs dash. Now you got why I discussed this one. I discussed this previous contents, that it will be useful at the time of comparison. Okay, here for rth moment, r dash, rth sth, two random, for two random variable it will be r s dash. Okay, suppose three random variable we have, then we can write r s k dash. Four random variable I can write r s k suppose t dash. Okay, three random variable also we are going to discuss, you just wait. Now this will be rs dash will be expectation of x to the power r, y to the power s, as here x to the power, expectation of x to the r only, here x to the power s r, y to the power s. This is for the continuous, and for the discrete will be I summation over I summation over j xi to the power r, yj to the power s, and the corresponding PMF. Now if we are going to consider r equal to 1, s equal to 1, okay, you just carefully you have to watch, here is somewhat interesting. R equal to 1 and s equal to 1 we are going to consider. That means what? In language this is nothing but your first and first product moment about the origin. See, first is for x, again first s is equal to 1, again first for y. So first and first product moment about the origin of the random variables, x and y will be what? Instead of r we have to write 1, instead of s we have to write 1. So here 1 dash will be equal to summation over ij summation over I summation over j xi to the power 1, yj to the power also 1, and the corresponding PMF. So what I am going to write for this one? This one is nothing but x to the power 1, y to the power 1 expectation. That is nothing but expectation of x into y, right? Expectation of x into y. Okay, this is nothing but your first and first product moment about the origin moment. This is also a moment. Have you got my point? See, in case of 2D random variable, whatever we have been discussed, this one is what? This is itself a moment. This is your first moment about the origin. This is also first moment about the origin. This is for random variable y, this is for random variable x. But this is what? This called as your moment, first and first product moment about origin of the random variables x and y. You got my point? So the name of expectation of x into y for the covariance whatever we have been discussed, this is nothing but your first and first product moment about the origin of the random variables x and y, right? Okay, now you just consider r equal to 1, s equal to 0. R equal to 1, s equal to 0, that means expectation of x only. Okay, that is nothing but first and 0th product moment about the origin of the random variable x and y. That means mu 1 0 dash will be summation over only x. Summation over only x, y to the power 0 will be 1, and x into p of x, because y has been considered as 0. That is what? Expectation of x. That is the first moment about the origin. Or we can say that first and 0th product moment of random variable x and y. You got my point? See, this one, expectation of x is nothing but is your first moment about the origin of the random variable x. If we have the two random variable x and y, then this ex will be also called as in some other language, that is your first and 0th product moment about the origin of random variable x and y, right? So if we are going to consider just reverse, r equal to 0, s equal to 1, then it will be mu 0 1 dash, that is your expectation of y. Okay, or you can say the first moment about the origin of the random variable x. Okay, okay, now we have to consider another one which is somewhat interesting. You see, now rth and sth product moment about mean. Okay, now rth and sth product moment about the mean, or it is also called as most of the books they have been written joint, so I suggest that you have to remember by this name. Okay, rth and sth product moment about the mean we are going to consider. Moment about the mean, or it is called as the joint rth and sth central moment. Okay, about the mean, that means about the mean also called as the central moment. So joint rth and sth central moment of x and y will be what we are going to write. You just recall for the one D random variable, one dimensional random variable, the rth moment about the mean or central moment is x minus x bar to the power r. So here we have the two random variables, so we have to write expectation of x minus ex is nothing but x bar. Okay, ex is nothing but x bar, ex whole to the power r into y minus expectation of y whole to the power s, or you can write expectation of x minus x bar, because ex expectation of x is nothing but x bar itself. So x minus x bar to the power r into y minus y mean to the power s. See, for single random variable it is only how much? X minus x mean or expectation of x to the power r. But for the two random variables, if we have, then this will be x minus x bar to the power r into y minus y bar to the power s. Okay, then this will be called as mu rs will be nothing but this one. So same thing, it has been, I have been written in this next page, that mu rs we found this one. Okay, now you consider, this is somewhat interesting and this is also important point. Okay, important point that you have to be just focus upon this. Now you consider r equal to 1, s equal to 1, r equal to 1, s equal to 1. So this will be how much? Mu 1 1, mu 1 1, that is nothing but expectation of x minus x bar to the power 1 into y minus y bar to the power 1, right? So what is this? What is this? This is nothing but your covariance. Okay, this is nothing but your covariance. You just see, this is nothing but what? Expectation of x minus x bar, y minus y bar, whatever we have previously discussed, x minus x bar into y minus y bar, that is nothing but called as the covariance of the two random variables. So here mu 1 1, mu 1 1 is nothing but your joint first and first central moment of x and y, or you can say joint first central moment of x and first central moment of y, is mu 1 1, is nothing but called as the covariance of xy, which is most important point of this discussion. Okay, so here joint first central moment of x and first central moment of y is nothing but mu 1 1, or that is your covariance, expectation of x minus x bar into y minus y bar, or covariance of xy. Or if you are going to be solve this, we can found expectation of xy, whatever we have in written previous, expectation of xy minus expectation of x into expectation of y. And what is this? What is this? This is your first and first product moment about origin. So here maybe you are going to be somewhat confirmed that whatever may be, either covariance we are going to consider, expectation we are going to consider, variance we are going to consider, the terms whatever we are getting, the terms, these all are the moments only. Okay, these all are the moments. So here xy, expectation of xy is a moment, ex is a moment, expectation of x is a moment, expectation of y itself a moment, and this one covariance of xy itself a moment, that is your mu 1 1, joined first central moment and first joined first central moment of x and first central moment of y. So here in one line I have been written joined first and first central moment of x and y, or you can write that joined first central moment of x and first central moment of y, is nothing but called as your covariance. Okay, now we have to go for three random variables. Okay, see, now consider yes, see, here we consider the r is equal to 1, s equal to 1. Okay, so you can consider anything, that may be r equal to 1, r equal to 2, s equal to 2, r equal to 1, s equal to 2, anything. Suppose you consider r equal to 1, s equal to 2, that then mu 1 2 will be called as what? First central moment of x and second central moment of y, right? So likewise 4 5, it will be fourth central moment of x and fifth central moment of y, right? Now we have to go for the three random variables. Suppose we have three random variables, that is your x, y, z, we have been considered three random variables. Now the joint first central moment of x, first central moment of y and first central moment of z, then will be how much? Here mu 1 1 is this one. Likewise joint first central moment of x, first central moment of y, first central moment of z will be how much? Mu 1 1 1 will be expectation of x minus x bar into y minus y bar into z minus z bar. Okay, okay, here x bar is nothing but expectation of x, y bar expectation of y, z bar is nothing but expectation of z. Now you just multiply whatever we have inside this. What we are going to get? You just multiply. Simply first multiply these two. We can get x into y, x um, x into y bar. Y bar is nothing but expectation of y. Okay, then minus x bar. X bar is nothing but expectation of x, y. Then x bar minus x bar minus y bar, nothing but your plus expectation of x into expectation of y into z minus ez. Okay, if we are going to be multiply these two, then we are going to get these terms. Carefully we have to watch. This will be xy into z, xy into ez, minus is there, minus, then here minus xui into z or xz into ui, like that. After multiplication we got this one, these terms. So again, further simplification, we found that mu 111 will be equal to, you can just pause the video and you write down. Okay, and mu 111 will be expectation of xyz minus expectation of x into expectation of yz minus expectation of y into expectation of xz minus expectation of z into expectation of xy plus expectation of x into expectation of y into expectation of z plus expectation of y into expectation of x into expectation of z, and these two terms will be cancelled out. So finally we found that mu 111 will be equal to expectation of xyz minus this one minus this one minus this one. These three terms I have been written, and these two terms are equal. Okay, so I can write 2 into expectation of x, expectation of y, expectation of z, right? So here this is nothing but called as your what? First central moment about of x, first central moment of y, and first central moment of z. Here you got that this is one term, expectation of xyz. What is this? What is this? If expectation of xy, if expectation of xy is called as your first and first product moment about the origin of the random variable x and y, if expectation of xy is called the first and first product moment about the origin of the random variable xy, likewise this expectation of xyz will be called as what? Will be called as first comma first and first product moment of the random variable x, y and z. Okay, so here you can see the rth or sth rth, sth, pth product moment. See here, this is your belongs to central moment mu 111, and this is what we found the product moment. Okay, so likewise you can consider the product moment, that the rth, sth, pth product moment about the origin, if you want to find out, of random variables x, y and z, then this will be mu rsp. Suppose dash will be expectation of x to the power r, y to the power s, z to the power p, summation over I, j. Suppose p varies, for variation of p we considered n. Okay, you just consider k, because here I written k. So this will be xi to the power r, yj to the power s, zk to the power p, and the corresponding PMF. PMF is your probability of x equal to xi intersection y equal to yi intersection z equal to zk. Right. Now, see the product moment about the origin. In general, we are writing this one like this. See, you can see mu for the two-dimensional random variable. Mu rs dash is your xi to the power r, yz to the power s. For three random variables, likewise we can consider here zk to the power p. Okay, so here we can say that rth, sth, pth product moment about the origin of the random variables x, y, z is nothing but this one. So here if we are going to consider r equal to 1, s equal to 1, p equal to 1, then what we are going to get? We can get mu 111 dash. That means expectation of x, y, z is represented by this one. And this is what? This is your fast product moment about the origin of the random variables x, y, z. What we intend to require for this one? To find out this one, we need this term. Okay, this is nothing but what? This is your first central moment of x, first central moment of y, first central moment of z. For this, to calculate this one, we need this term. Yes or no? And this term is nothing but your fast product moment about the origin of the random variables x, y, z. And this is your expectation of x. That means first moment about the origin of the random variable x. And this is what? This is your first product moment about the origin of random variable y and z. And this is what? This is your first moment about the origin of the random variable x. And this is the product moment, this is the first moment, this is the product moment. So here from this expression itself, we can conclude that whatever the moment we are going to be extract, these all are connected with each other. So here, to find out the central moment, we need the moments about the origin. Okay, so if we are going to here from this point, we found that covariance is itself one moment. Okay, uh, and expectation of any random variable, we know we know that is also a moment about the origin. Variance also another moment. Okay, now we have to go for the multivariate moment generating function. Okay, up to this much we have been discussed about the different kinds of moments whatever we can found from for a bivariate distribution. For that we considered the two examples, that is your second two-dimensional random variable, and here three-dimensional random variable, three random variables. Likewise you can consider multi random variables, and you can found the different kinds of moments. Now we have to go for the multivariate moment generating function, which will be required for our multinomial distributions function. Multinomial distribution. Okay, so here you can see the m.g.f moment generating function of n random variables. We just discussed two-dimensional or two random variable, three random variable. If we have n random variables, not n, k. Okay, let k random variables. We have, suppose k RVs such as x1, x2 up to xk. The m.g.f of k RVs will be, in general, a moment generating function is written as m capital XT, that is your e, expectation of e to the power t into x, but here we have tried t dash into x, e to the power exponential of t dash x. So here expectation of e to the power, this t dash is nothing but t1, and this x is nothing but x1, x2, x3 like that. So here t dash x will be nothing but exponent to the power t1 x1, t2 x2 up to tk xk. For single random variable it will be tx, but for your multi uh, random variables if we are going to consider, then it will be expectation of exponent to the power t1 x1 plus t2 x2 plus so on tk xk. Okay, so it can also be written as, instead of x, in generally many books they have been written that uh, capital M subscript of x1 x2 up to xk, function of t1 t2 up to tk is equal to this one. Okay, is equal to this one. Okay, so I suggest you have to write in two way, but you just remember this one, this equal to this one, and this e to the power t1 x1 plus t2 x2 up to tk xk can be written as summation over I equal to 1 to k. See, expectation is there, expectation exponent to the power summation over I equal to 1 to k ti xi, right? So here I uh, it starts from 1 to k number of random variables we have. Now particularly we have to consider two random variables, x1 and x2. Okay, see here we are considering the random variables as x1 x2 x3 like that, but previously we have been considered that x y z, don't be confused. That means here x means your x1 x2 x3 like that. Okay, instead of considering xyz we can consider x1 x2 x3 like whatever we have been we considering here. Okay, so now we are going to consider two random variables x1 x2. So mxt or m x1 x2 function of t1 t2 will be how much, expectation of e to the power t1 x1 plus t2 x2, right, will be equal to summation over r equal to 0 to infinity summation over s equal to 0 to infinity t1 to the power r1 by r factorial into t2 to the power s by s factorial into expectation of x1 r into x2 to the power s, x1 to the power r into x2 to the power s. So here the coefficient of t1 to the power r by r factorial into t2 to the power s by s factorial is nothing but your mu rs dash or rth and sth product moment about the origin of rv x1 xp. See here what we done, we are trying to find out the moments with the help of the moment generating function. But previously whenever we have been discussed the two-dimensional random variable, traditionally we have been discussed, this is your mu r s dash, and here we are trying to find out the same rth sth product moment about origin of rv x1 and x2. Okay, now so here suppose you are going to be think that the expectation of x1 x2 should be the coefficient should be t1 to the power 1 t2 to the power 1 by 1 factorial into 1 factorial, is it so? Or t1 to the power 1 t2 to the power 1 by 1 factorial into 1 factorial has to be give expectation of x1 into x2 or the first product moment about the origin of two random variables x1 and x2, is it so? Yes. See if we are going to be expand this one, e to the power t1 x1 t2 x2 here you just write by simplification. Simplification. So the simplification I have been done here. The expectation of, you just e to the power this one, e to the power x, you just consider e to the x, that means 1 plus 1 by 1 factorial of this one, plus 1 by 2 factorial to the into this term to the power 2, plus 1 by 3 factorial into this term to the power q, and so on, right? So expectation symbol is there. Now this will be 1 plus 1 by 1 factorial, uh, okay, okay, you just do one thing, that you just apply the expectation for this one. Expectation I have been applied over 1, this will be 1. Expectation I have been applied over this term and this term, this term and this term, t1 by 1 factorial expectation of x1, t2 by 1 factorial expectation of x2. Okay, and so here you can see this is the t1 x1 plus t2 x2 square, so it will be t1 square t x1 square plus t2 square x2 square plus 2 into t1 t2 x1 x2, right? And this is t1 x1 plus t2 x2 whole cube, so t1 x1 whole cube, that means aq, plus this is your bq, t2 cube x2 cube, okay, plus 3a square b. 3a square means 3t square x square. Suppose this is your a, t1 x1 is your a, so 3t square x square into b, t2 x2, and 3 ab square, t1 x1 into t square x square, okay, and so on. So this is your first term, 1 by 1 factorial t1 x e expectation of x1. This is your second term, whatever I have written, and again I am going to apply the expectation of for this and this. It will be 1 by 2 factorial t1 square, here I not written expectation of x square, 1 by 2 factorial t2 square. This is your also expectation of x square, I not written expectation, expectation of x square, you just do it in your rough, okay. And this will be you can see 2 by 2 factorial, will be 1 by 1 factorial, I can write 2 got cancelled, and this will be expectation of t1 t2 x1 x2. This is most important. t1 t2 expectation of x1 x2, okay. Now this is 1 by 3 factorial, this one, that means 1 by 3 factorial t1 q expectation of x1 q, okay. This is 1 by 3 factorial t2 q expectation of x2 q, expectation of x2 cube, and this is 3 factorial, 3 factorial, see here this is there is no 3 factorial, 1 by 3 factorial and 1 by 3 factorial, but here 3 is there, so 3 by 3 factorial is nothing but 2 factorial, right? So 2 factorial into t1 square and t2 expectation of x1 square into x2. Likewise here 1 by 3 factorial into this term, that means will be 1 by 2 factorial t1 into t2 square x1 x2 square, expectation of x1 x2 square, and this term is not there, this term already I haven't written over here. So these are the terms. So here you can see that suppose we are going to consider this term, so this term can be written as 1 by 1 factorial into 1 by 2 factorial into t1 to the power 1 into t2 to the power 2 expectation of x1 to the power 1 x2 to the power 1. So this is what, this is your first and second product moment about origin, yes or no? Okay, so what is this? This is what? This can be written as 1 by 1 factorial into 1 by 1 factorial t1 t2 expectation of x1 x2. This is what? Expectation of x1 x2 is nothing but your first and first product moment of random variable x1 and x2, and this is nothing but is the coefficient of t1 by 1 factorial t2 by 1 factorial. Okay, whatever here is written, that t1 to the power 1, if we want first and first moment, t1 to the power 1 by 1 factorial, t2 to the power 1 by 1 factorial. So here t1 to the power 1 by 1 factorial, t2 to the power 1 by 1 factorial, coefficient is nothing but expectation of x1 x2. You got my point? Okay, see, if we are going to be find out the expectations and other moments by using this method, it is somewhat lengthy, but we have to consider the moment generating function to find out the moments. So here the coefficient of, in general we can write t1 to the power r by r factorial, t2 to the power s by s factorial will be give you, the coefficient will be give you mu rs dash or rth and sth product moment about origin of rb x1 and x2, right? Now here if we consider r1 and s1, that we are going to get mu 11 dash whatever we haven't discussed. Now we also consider as e x1 to the power r x2 to the power s is nothing but del of r by del of t1 to the power r. This method, whatever I'm going to say to you, already told to you, and this is derivative method. So here single random variable, so dr by d dtr of mxt, but as we have two variables, so we have to consider del r moment generating function of two random variables by del t1r and del s del to the power s moment generating function by del t2s. Okay, after that, or we can write that del of r plus s, del power r plus s of moment generating function by del t1 r into del t2 to the power s. After this we have to consider all the t will be 0, t1 will be 0 and t2 will be 0. Now suppose we are going to consider r equal to 1, s equal to 1, then e x1 x2 1 1, e x1 x2, that will be here r1 r s will be 1 1, so del square m x1 x2 moment generating function of the two random variables by del t1 into del t2. After that we have to consider t1 equal to 0, t2 equal to 0. Okay, likewise you have to consider, suppose t2 equal to 0. T2 equal to 0 means we have only single random variable, so exponent to the power x1 to the power r. See, if we have t2 is 0, that means x1 x2 automatically will be not to be considered, so it will be m x1 t1 by del t1 to the power r, t1 equal to 0, t2 equal to 0. That means here this will be called as rth moment about the origin. Likewise, if we are going to consider 1, then it will be expectation of or first moment of the random variable 1. Likewise, if we are going to consider only t2, t1 is not there, so it will be expectation of x2 or first moment of the random variable x2. Now covariance, if we are going to consider covariance x1 into x2, x1 x2, so covariance, if we are going to consider in between these two random variables, we need expectation of x1 x2 minus expectation of x1 expectation of x2. So in this way we can found expectation of x1 expectation of x2 and expectation of x1 x2. So all the moments, this is called as the first product moment of x1 x2 about the origin. This one is called as your what, This one is your first and zeroth product moment of x and y. This is your called zeroth and first product moment of x and y, random variable x and y. Okay, so by using moment generating function also we can found this so called covariance. Okay, this will be easy as compared to this one, right? So in general, if we want uh, if we want to find if we want to found out if we want to found out covariance between any two random variables, then covariance of xi xj will be expectation of xi into xj minus expectation of xi into expectation of xj. So hence by choosing mgf we can found any moments by using mgf. Hence by using MGF we can found any moments. This is not correct for multivariate distribution. Here we concluded. Okay, next here next now we have to consider moments of multinomial distributions um, with the help of moment generating function. So first of all we are going to be find out the moment generating function of the multinomial distribution. Okay, then we have to find out the moments. So as we discussed that for the multivariate moment generating function, this will be expectation of e to the power x1 t1 x1 plus t2 x2 up to tk xk. So here uh, we have to, in general we have to write that the moment generating function of multinomial distribution will be written as mxt or m subscript of x1 x2 up to xk function of t1 t2 tk, that is your expectation of exponent of summation of I equal to 1 to k ti xi, right? Same thing here, exponent of is written like this. Here it is written e to the power summation of this one, same thing. So here, so this is nothing but your summation over x is equal to 0 to n. Here n is the number of trials, this one, sorry, PMF into this one. We know that in previously also we know that you can recall itself a moment generating function about the hypergeometric distribution, that exponent of e to the tx is nothing but e to the power tx into PMF. For all the distribution the same procedure, that is e to the power tx into PMF. So here the PMF is nothing but what, in our last class we have been discussed that the PMF of uh, the multinomial distribution is nothing but this one, n factorial by x1 factorial into x2 factorial into xk factorial into p1 to the power x1 p2 to the power x2 up to pk to the power xk. And that same PMF I have been substituted over here into exponential of this one, same thing I have been written over here. Now it will be summation over x equal to 0 to n factorial by x1 factorial into x2 factorial up to xk factorial. And this you can see this is your p1 to the power x1, and here if I'll be expand this one, it will e to the power t1 x1 plus e to the power t2 x2, like that. Sorry, this will be e to the power t1 x1, see this is nothing but e to the power t1 x1 plus t2 x2 plus t3 x3 we can get, and so on. So here also you can write e to the power t1 x1 into e to the t2 x2 into e to the t3 x3, and so on. Okay, here one term we can consider e to the power t1 x1, here p1 to the power x1, so we can write p1 to the power e to the power t1 to the power x1. Here one term is p2 to the power x2, another term you can found e to the power t2 x2, you just expand this one. Okay, e to the power t1 t2 x2, so p2 into e to the power t2 to the power x2. Okay, and so on pk e to the power tk x to the power k. Okay, okay, see this exponential things, if we are going to expand, what we are going to find out, this will be t e to the power t1 x1 plus t2 x2 up to tk xk, or you can write e to the power t1 x1 into e to the power t2 x2 up to e to the power t1 xk a tk xk. Okay, so here e to the power t1 x1 p1 to the power x1, we can write p1 into e to the power t1 to the power x1 like other terms. Okay, so I have to erase these things. So now uh, here is the important thing, is that this can be written as p1 into e1 to the power t1 plus p2 e2 to the power t2 and so on pk to the pk into e to the power tk to the power n. How it is, in our last class we have been discussed. See, you can check the last class video, that in detail we have been discussed that how this will be this. See, in detail we have been discussed that uh, this this value n factorial by x1 factorial x2 factorial xk factorial into p1 to the power x1 p2 to the power x2 up to pk to the power xk will be, how will be this much, in detail we have been discussed. In the same procedure here, this is p1 to the power x1. Here instead of p1 it is p1 into e to the power t1, right? p2 e to the power t2, pk e to the power tk. So instead of this, what we can write? We can write p1 e to the power tn. See, p1 p2 p3 up to pk to the power n we have been written. How it is, you just check the last video, in detail we have been discussed. Okay, so likewise this can be written as p1 into e to the power t1 plus p2 into e to the power t2 up to pk to the into e to the power tk to the power n. So this is represents the m.g.f, moment generating function of multinomial distribution. So here x is the random variables x1 x2 up to xk. Now if we are going to consider, we no need all the random variables, we need one random variable x1 corresponding t1. So this will be m1 mx t1 and all others are 0. And if I am going to put t equal to 0, instead of t1 others I have been substituted 0 0 0. So we can find p1 into e to the power t1 plus p2 p3 up to pk to the power n. Okay, so mx1 t1 will be equal to, see, this one for e to the power t1. Okay, and previously we know that p1 p2 p3 up to pk, but all summation of all the probabilities is 1 minus p1. See, this term is here, except this term other terms are nothing but 1 minus p1, because if I add all the probabilities the value is 1. Okay, so p1 plus p2 p3 up to pk is equal to 1. So p1 p2 p3 up to pk will be how much? This much will be 1 minus p1, 1 minus p1. So instead of this I can write 1 minus p1, right? 1 minus p1 is nothing but q. 1 minus p1 plus p1 into e to the power t1 whole to the power n. So if we have to consider the binomial distribution where two outcomes are there, so here that will be p1 minus p. You can check your note for binomial distribution. moment generating function is your q plus p into e to the t to the power n. So here 1 minus p1, so you consider p1 is your success. So 1 minus p1 is belongs to q. This is p1. Instead of p1 we can write p, and e to the power t1 can be written as e to the t to the power n. So here whenever the multinomial moment generating function is reduced to single random variable, it is transformed to your binomial distribution. Okay, as I told that this is the generalization of your binomial distribution. This distribution can be considered a generalization of binomial distribution. Here we have been proved. Okay, so if in your exam it is asked that you have to prove that this is a generalization for binomial distribution, you have to write up to this to this, from this to this. So using moment generating function you have to prove this one. So this is your this is nothing but your reduced moment generating function whenever you are going to consider only a single random variable, which is equal to your moment generating function for binomial distribution. Okay, so therefore by considering mgf one can determine any moments for any number of RVs, as we have been discussed. So okay, so by considering moment generating function we can found any moments, right? Now we have to go for the we have to consider this moment generating function for multinomial distribution, and we have to find out some moments. You just watch. Okay, what are the values? Okay, here we are going to be consider two RVs, two random variables x1 and x2, suppose. So mxt will be mx1 x2 t1 t2, that will be p1 into e to the t1 plus p2 into e to the t2 to the power n. Okay, by considering this one moment generating function, by considering equation number 1, you can write by equation number 1. By equation number 1 we can found this one. Now ex1 x2 fast, that means this is what, fast and fast product moment of x1 and x2 about origin will be what, del square m x1 x2 t1 t2 already we discussed, divided by del t1 to the power 1 del t2 to the power 1. After that we have to consider t1 equal to t2 equal to 0. So that means moment generating function whatever we have, first we have to differentiate with respect to t1, then we have to differentiate with respect to t2. So first I have to differentiate with respect to t1, it will be n p1 p1 into e to the t1 plus p2 into e to the t2 to the power n minus 1. Second time derivative if I am going to do with respect to t2, then I can found, you can see n into n minus 1 with respect to t2 means p2. Already p1 is there, so p1 into p2 and this much to the power n minus 2, right? Now we have to put t1 t2 equal to 0. So this will be 1, this will be 1, e to the 0 1, e to the 0 also 1, so p1 plus p2 to the power n minus 2. We know that total probability is 1, so p1 p2 is 1 to the power n minus 2 anything, 1 to the power anything, that means n minus 2 will be 1. So we found this one e x1 x2, that means first and second product moment of x1 x2 about origin is this one. Likewise if we want to expectation of x1, that means we have to consider the first derivative with respect to t1 and then t1 will be 0. Now if we are going to consider first derivative, then this will be the value n into p1, then you just put t equal to 0 0 0, so p1 plus p2 plus p2 is nothing but 1 to the power n minus 1 is 1, so we got n p1. And second if we are going to consider expectation of x2, then derivative with respect to t2 equal to 0, we can get n into p2. Okay, now if we want to find out the covariance of x1 x2, that means joint first central moment of x and first central moment of y, joint central moment, that means is your covariance of expectation of xy minus expectation of x into expectation of y. This value will be, already we found, n into n minus 1 p1 p2 minus this one into this one, expectation of x, x see it is here you have to write x1 x2 x1 x2, okay, x1 x2. So this will be x1 into x2, x1 into x2, that means n p1 n p2, n square p1 into p2, and after solving we can get minus n p1 into p2. So in general covariance we can write for this multinomial distribution, because from the moment generative function of multinomial distribution we found this one, right? So for covariance of any random variable, any two random variable, if you are going to be you are trying to find out, then n into n minus 1 pi pj minus n square pi pj will be minus n pi pj, you can found. So here you can see again you conclude that the expectation, variance, covariance are the only the moments, right? Now we have to go for very general. So in general, suppose we have k number of random variables, that is k1 k2 k xk. So mxt in general we can write this one, whatever we have been written over here. And now we want to find out fast product moment of about the origin of x1 x2 up to xk. Okay, then what we have to do, we have to do the first derivative of moment generating function with t1, again derivative with respect to t1, again derivative with respect to t3, again derivative with respect to tk. That means del to the power 1 plus 1 plus 1 up to k times, divided by del t1 into del t2 into del t3 up to del tk. Then after we have to put all t equal to 0. So if we are going to consider del k, that means here 1 plus 1 plus 1 up to k, that means del k m by del t1 del t2 del t3 up to del tk. So k times, if I am going to derivative this one, then how much I am going to get? I can get n into n minus 1 into n minus 2 into n minus k minus 1. Okay, you just see that whenever we differentiated two times we got n minus 1. Okay, likewise if we are going to differentiate k time, then the last one will be n minus k minus 1. And probabilities also we are going to get p1 p2. So here k times derivative means p1 p2 p3 up to pk, and these terms will be p1 to the power t1 up to p2 to the power t2 up to pk to the power tk. If we have to put t equal to 0, all t equal to 0, so this bracket will be p1 plus p2 plus pk to the power n minus k, as all the probabilities adding after addition all the probabilities were 1, so this will be automatically 1. And we found expectation of x1 x2 x3 up to xk is nothing but n into n minus 1 into n minus 2 up to n minus k minus 1 into this one into this one. So this is what, this is nothing but your fast product moment about the origin of x1 x2 and so on xk random variables. So here we have been in general is discussed. That means with the help of the moment generating function you can determine any type of moments, any type of moments. You can determine covariance of two random variables, or covariance of three random variables, or four random variables, or the so-called fast product moment, or you can find out the first, second, third, fourth product moments, anything. Okay, so this is all about your moment generating function and moments of multinomial distribution. I suggest that you have to go through the video carefully, you have to watch carefully and pause the video. You have to write down the notes, whatever the extra things, previous study things, whatever we discussed initially, those things no need to write in your note, but you have to write down this one. And first we have to discuss this one, then you have to write down these things and these things also, whatever we discussed. Okay, so thank you so much for watching this video. In our next class we are going to be discuss a few numericals based upon your multinomial distribution. Okay, thank you so much for watching this video. Thank you.